Hi, this is Dave Farmer. We're having a webinar today with a fellow called Norm Bartlett. He is the CEO and president of Creative Sensor Technology, and they are makers of flow sensors and flow sensor related equipment. Flow sensing is becoming quite an issue nowadays for water savings because it allows your system to know what the flow is. So if you have a broken pipe or a broken head, the system can be alerted, thus you have less loss in many, many ways, not just of water, but damage and all sorts of things. And more and more irrigation designs are requiring a flow sensor and probably a master valve combination. And so it's good to kind of see what's going on out there in the world with this sort of technology. And it'll be interesting to see what Norm has to show on this. So if you have any questions, you can type it in the message box there on the GoToMeeting dialog box. I will monitor any questions that may come across and relay them to Norm. But what I would like to do is to make Norm now the presenter of this. So Norm, it's good to see you this morning.
Well, thank you, Dave. It's good to be aboard, and thank you everybody for attending. I can promise you this: my flow sensors work better than my computer.
Okay.
And right now we seem to be ready to go. Can you see my opening slide on your screen?
Yes, I can. Everything looks good, Norm.
Okay. Well, I'm sorry for the delay, folks, but let's get started a little bit. And as Dave had mentioned, we're going to talk a little bit about flow sensors this morning. And in the irrigation industry, what we're going to talk about a little bit is the fact that, boy, I don't know why this thing is running so slow, but the program here it is all becoming about water management. And what we're finding out is that what used to be called an irrigator is now a water manager. So we're going to talk about how flow sensors can help in that process, and basically we're going to talk about how flow sensors interface with smart controllers. Now, I don't know exactly, where the education level is of our audience, so just for those of you who might not know, let's review the idea of a smart controller a little bit. And a smart irrigation controller is really one that goes beyond being a simple timer. It's a device that is now connected to a lot of different input sensors, such as rain, could be moisture sensors, it could be a weather sensor, or it could download ET information or weather information from a remote weather site and use that information, either ET data or soil moisture or things like that, to control how often and how long the irrigation zones actually operate. The other thing that smart irrigation controllers also have is the ability to communicate, and they not only can react to the input of these sensors and control the time of the running of the zones, or even perhaps shut the system off in cases where water is not needed, but they also transmit that information via the internet, paging devices, Ethernet devices, things like that, to a central computer. And that central computer may or may not be in the manager's location. He may still be in another remote location talking to it via mobile phone, or even an iPad or some type of device like that. So a smart controller basically is something that does a lot more to control the watering of the system than just turning it off and on based on time. They also have the ability to log data and do a lot of reporting and logging types of information. This happens to be a screen that we're showing on a smart controller made by Weathermatic. And you can see that it has all of the zones set up. Flow is enabled on all of them. This happens to be a flow screen. We're enabling flow reading on all but zone 10, and we can put in here zone low flow limits and high flow limits. We also, if you notice up here, there is a time to fill the lines. That's a time delay so that there isn't any kind of an alarm condition basically too soon. So these screens are available. This is only one of many different types of things that a smart controller can do in the process of using flow. So we're going to go now and say, all right, that's kind of the condition of it, but let's talk about how the sensors are used. And primarily, let's start by saying they're used to conserve water and to prevent water losses. Typically, we use flow sensors to detect leaks in the irrigation system, and they can be large and small. We can also use it to find stuck valves. And a stuck valve shows up in the scheme of things as all of a sudden when the valve that did not shut off remains on and the next valve in sequence comes on, there's a dramatic rise in the flow rate. So that gives the controller some indication that there's a flow problem. Typically, they then will advance to another station, and if the condition continues, then they might cancel the whole watering program and send an alarm message. The other thing that the smart controller can do is find valves that aren't working. If solenoids fail, wires get cut, or some other problem happens to the zone valve itself, it shows up as no flow, and again sends an alarm message to alert the operator that there's a problem with the system. The other thing that it can also do is typically sense unscheduled flow. And when we talk about unscheduled flow, we talk about any event where flow is running when the controller is not calling for water. This can be anything from a maintenance person using a hose bib or a quick coupling valve and running water in large amounts when it's not supposed to be running, or again it could be a pipe failure or a valve failure. So we conserve water hopefully by preventing some of these losses. Now let's talk a little bit about catastrophic losses like a pipe break. This, if you can see my pointer, this happens to be an individual standing here on the side of the fairway. If he's 6 feet tall, this water is shooting probably 25 feet in the air at least. This is an 1.5-inch line. A broken 1.5-inch PVC pipe running at 50 psi can discharge 10,000 gallons in 30 minutes time. Looking at it a different way, if it ran for 8 hours, say overnight with nobody noticing it, the loss would be 168,000 gallons. And to put that in another way, that's enough to cover an acre of land to a depth of 6 inches. So we're talking about all of the water conservation measures that you might have incorporated into the design of a system going out the window in one overnight catastrophe. So that's what happens with pipe breaks. But there's even smaller, more subtle things. We can have a small leak, just like a cracked or a split riser on a spray head. That can discharge, say, 15 to 20 gallons a minute. Or again, 200 gallons every 10-minute cycle that zone is supposed to come on. Or we can look at it as 800 to 1,000 gallons per week, depending on the amount of times that zone runs per week. Or again, we look at it as 25,000 gallons of lost water per season. That's one split riser on one spray head. So we can see how these things can add up and become very significant water losses. But in addition to losses, we also get into some other things. This little note down here on the bottom, what if it's somewhere you can't see it? More and more times we have a water manager, whether he's working for a city, a college, a industrial park, or a residential housing facility. He's not on the job walking the grounds every day of the week. So these things could occur over a period of time, and it wouldn't be until maybe a mowing crew or somebody else came and noticed that before it was really noticed and repair action was taken. This is the advantage to having a flow sensor on a smart controller system. But we also get involved with public safety. We can have broken pipe, failed sprinkler heads and things like that spray water onto roadways, traffic areas, things like that, and become a hazard. Can become a surprise to a driver, cause an accident, and create, a public relations and public safety nightmare. So again, obviously we want to prevent these things. Even if it wasn't a concern about losing water, we'd want to protect the property from that way. And speaking of property protection, we also get into property damage. Obviously, a broken pipe doesn't have to be a catastrophic leak. It can leak underground, and depending on soil conditions, we can wash away a hillside, we can collapse a retaining wall, we could actually even flood a freeway or something like that, or we could end up with half of this person's backyard being down on another level on a street below. So all of these kinds of things are reasons to use flow sensors from a protection standpoint. But there's also, we use flow sensors to manage water usage. And by managing that, we're obviously looking at totalizing flow. This is the record keeping and the management side of this. We can look at flow and compare it month to month, year to year, compare it with weather records. And again, some of these smart controllers, like the one I showed you, have the ability to graph, let's say, water usage with temperature, or you could graph fertilizer usage or pesticide usage with flow, and you get a better sense of being the manager of the property as to how to use flow as part of your management scheme. There's also regulatory reporting requirements, and by having a flow sensor built into a smart control system, it generates these reports, and you can pull reports for daily, monthly, seasonal usage. The other thing that it does as a sidelight is to verify the operation of ET or moisture sensors. Somebody can say, well, how do we know we're actually saving water? How do we know that the watering is less than, say, my every other day or every third day schedule? You look at it by, again, looking at the usage graphs and looking at them to make sure that in hot, dry weather the irrigation system is coming on, but in cool, cloudy days that it's staying off, or that you're looking at moisture sensors really controlling the amount of watering based on the moisture in the ground. So they come into play several different ways. And this is more critical with reclaim or reuse water or alternative water supplies, because in addition to maybe keeping track of things, any of you that have used reclaimed water know that it needs to be either proportioned or blended with fresh water, or it in some cases may need treatment. There is always a need for pH adjustment, salinity adjustment, things like that. And they are always usually volumetric and depend on measuring the amount of water that's flowed through the system to decide how to proportion or how to treat reclaimed water. So there's the reasons why to use flow sensors. Now we sit there and say, I'm gonna give you a little brief look at why I think you should be using creative sensor technology flow sensors. And we start off with the first one is that this is our product is the first new flow sensor design in decades. And just like sprinkler heads and smart irrigation controllers and management techniques, we improve things over time. And ours is a new, fresh start with a clean sheet of paper, and it obviously has some advantages. Our flow sensors are compatible with all irrigation controllers that are ready for flow. There isn't a manufacturer's device on the marketplace that cannot use our flow sensors, even though they may sell a different brand themselves. We're also the only ones that have designed the flow sensor from the ground up for the irrigation market. We have no other market share that we sell flow sensors in. This is our entire business, so everything we do with the flow sensor is geared to this service. And a lot of times that means making it rugged enough to live in the environment underground, making it simple to service, and making it more user-friendly than some of the industrial devices on the market. And because we've designed it for the irrigation market and from the ground up, we get better low flow performance. And this is the critical part of the flow sensor, is that it will measure and detect low flow for a couple of different reasons. One is that the lower the flow that it will detect, the better its ability to detect leaks and oftentimes things that are happening when they're not scheduled. If a flow sensor can't see a 5 or a 10 gallon a minute flow, then it's not going to be able to detect a very slow leak or a hose bib that's been left on by a careless worker. The other thing is that in all irrigation technology today, all of the advancements have been to using less water. That means we're doing more with drip systems, we're doing more with MP rotator type nozzles, we're doing things to reduce the flow rather than increase it. So we get to the heart of the matter by getting to a much lower flow rate than anyone else. We also design the device with higher pressure ratings so that our flow sensors can withstand better pressure than some of the others that are currently available. And because we've designed it in the way we have, there's virtually no friction loss through it. And friction loss through any device, whether it's a water meter, a backflow preventer, an automatic valve, it's a necessary evil, but think of it as driving around with one foot on the gas and your other foot on the brake. The more friction loss you have, the more energy is required to produce, water through a piping system. So the more we can reduce friction, the less money we spend on electricity or pumping costs. Also, because we've designed our sensor with all of our own custom designed materials, we get measurement accuracy and repeatability. We mold everything from our own custom molds. We don't use things that are adapted or machined from other products, and we get a better rate of accuracy and much more consistency, or what we call repeatability. We've also tried to make the installation simple, and I'll show that in a couple of pictures of slides. And finally, we've designed it for long service life. It lives in a tough environment, being in a valve box underground. And what we've tried to do is ensure that the electronics inside the device are as protected as well as we can possibly make them. And we've proven that with some long-term life cycle tests where we've actually had sensors running in a tank under 6 feet of water, continual service for over 2 years with no signs of leakage into the electronics. So that's why we want to use our types of sensors. Let's take a look at what they actually look like. Our flagship unit, if you will, is a T-type sensor. It's made out of PVC. It has socket ends for solvent welding into systems, available in inch, inch and a half, and 2-inch sizes. And it really is fairly simple. It consists of 3 parts: a mounting T that goes into the piping system, the brains of the device, which we call an insert assembly. That contains this little rotating impeller, and it contains the electronics that detect the flow and amplify it and send it out on this 2-wire path. And then the third part of it is this big retaining nut that holds the assembly into the T. Now, when we look at a cross-section of this, what you can see is 3 pieces. Here's the T, here's the assembly, here's the retaining nut. But all of these have been designed to work together, and we end up with a very smooth water path through this T. This small impeller turns as the water flows by it with very little friction loss, because really what we're doing is we're putting water through this wide open space. By doing that, we have low friction, and we have the ability to detect low at flow rates. We try and make it easy to install by keying everything, if you will. There is a key on the outside of the insert assembly that fits into an alignment slot on the T. Even reaching down into a valve box, it's easy to set this thing to the right alignment, having it nice and square in the T, and it automatically sets it to the correct depth. So again, there's no variation from one T to the next as to how it's going to read flow. And this insert assembly, by the way, is common to all devices. This one insert will fit in any one of our T's, so it makes even exchanging parts simpler and easier for the technician in the field. Now here's just a quick little installation shot of what it looks like in the ground. This installation detail is actually one that I've pulled right out of the LandFX library. So this is the kind of installation detail you get with LandFX designs. This shows the flow sensor in a valve box below grade. It identifies the type of wire splice connections. It identifies the type of wire that we want to use, and it also points out the fact that the sensor can be as far as 2,000 feet away from the controller. So a lot of detail information on here, and one last thing to point out is I want you to see that we also recommend on this that we have 10 diameters of straight pipe ahead of the sensor and 5 diameters of straight pipe downstream of the sensor before there's any change in pipe sizes, any T's, or anything of that nature. And the reason we do that is that we want the flow to be straightened out and not turbulent and not surging and not doing anything as it goes through the sensor. So you're going to see this 10 and 5 rule with practically everyone's equipment. It's always a requirement, and it's always the best practice to put this in with straight pipe going in and out of the device. Now we also make a device like this for the larger sizes. We make a saddle type sensor. We're all set to produce a 3-inch PVC T, and then conversations with installers and designers, and they said, you know what, you start getting into 3- and 4-inch size material, it's tougher to solvent weld, it's tougher to cut pipe. So if it was in a saddle type of mount, it would make it much easier to install. So this saddle contains the same insert assembly with the same mounting device, but it clamps over the pipe, and the installation is made easier because really all one has to do is, again, find a nice straight piece of pipe, drill an 1.5-inch diameter or 1 3/4 inch diameter hole in the pipe. This O-ring on the underside of the saddle seals this, and the flow sensor housing protrudes down into the pipe and carries the little impeller down into the flow. There's nothing else to buy. We don't sell the sensor separate from the saddle. It's all one unit. And again, we're preset to the right depth and the right alignment. So again, it makes it easy to install, simple for the contractor in the field. You put the saddle on the pipe, and then you put the insert into the top branch of the saddle, and you screw down the nut, and you're ready to go. So that's pretty much how those things work. Let's talk a little bit about where you actually install a flow sensor in the system. And what we'd like to point out here is we've got 3 basic rules. Number 1 is always locate the flow sensor as close to the source as you can. Most code requires that you put nothing ahead of the backflow preventer. The RP unit or whatever you're using is as close to the street as it can get, and typically code officials will say anything involving the irrigation system has to be installed downstream of that. So we want to put the flow sensor and the master valve, and the master valve is nothing more than a diaphragm or solenoid type of control valve that allows you to shut off all the flow in the system. it will shut off everything going through the main feed. So if there is some kind of catastrophic problem, the smart controller can close the master valve and prevent anything downstream of it from leaking. Obviously, we want to put the flow sensor in the master valve as close to the source as we can, so there couldn't be anything ahead of it that could be leaking. We also want to make sure that the flow sensor is close to the source, so we measure all the flow that's going into the system. Now, one thing I'm going to point out here is two things. First of all, is notice we're talking about 10 diameters between the master valve and the flow sensor. And the reason for doing that, again, is to get this straight pipe to reduce the turbulence and improve the accuracy. Again, on the other side of the flow sensor, we're asking for 5 diameters of straight pipe. And then after that, if the pipe needs to elbow or tee, or there needs to be some other kind of fitting on here, that's fine. But try and maintain this 10 and 5 rule. And that's diameters of pipe. If this is an 1.5-inch flow sensor, this is 15 inches, and this is 7.5. If this is a 3-inch flow sensor, then this is 30 inches of pipe, and this is 15. So that's the kind of thing we say when we say 10 and 5. The other thing that I noticed in here is the master valve is ahead of the flow sensor. Does it make any difference? Not really. And you will see that some designers will put the flow sensor before the master valve, others will put the master valve upstream of the flow sensor. Really, if the master valve closes, it's not going to measure flow on this side or on this side. So it really makes no difference. It's strictly a preference of the designer. Rule number 2, if we can get my device to move, is that we design a flow sensor, we pick the size of it by the flow, not by the line size. And the reason we do that is that a flow sensor, let's take a look at this chart. Here are 5 different size flow sensors. This vertical column here is in velocity, or feet, measured in feet per second. Now, most of you who have designed systems will get used to the idea that the typical maximum design through PVC piping system is limited to 5 feet per second. Above that, we get into phenomena called water hammer that creates damage to the pipe, possible surges and bursting and things like that, and they increase with distance, with pressure, and with velocity. So we try and keep velocity to a 5 foot per second range. Flow sensor is not pipe. Even though it's made out of PVC, it's typically made to withstand much higher rates of velocity through it because it's going such a short distance. So if you'll notice this, we rate the maximum velocity of our T-type sensors at 15 feet per second, and we rate the maximum velocity of the saddle-type sensors at 12. This is design criteria. This is fine. So what we want to do is we want to size a flow sensor to the size of your largest zone or your greatest demand. And if the greatest demand is in the range of 50 to 75 feet per second, we have no problem, or 50 to 75 gallons per minute, we have no problem using an 1.5 inch flow sensor, where you might want to use a 2 or even 3 inch PVC pipe size. So always design the flow sensor to the gallonage and not to the pipe size. You may have similar criteria to automatic valves. You can oversize an automatic control valve. A solenoid diaphragm type valve will not work unless there's some friction loss through it. So there is a point at which you can have a size of a valve that's too large to operate. So always remember this rule.
We have a question, Norm.
Sure.
On that, back at that previous chart.
Okay.
The question was, are the figures you're showing here the maximum flow allowed by the size of the flow sensor?
The minimum flow is what we can detect as the lowest flow rate in gallons per minute, and the maximum flow down here is what we'd say would be the maximum allowable flow through the device. 1-inch flow sensor, you probably would never want to exceed 50 gallons a minute. Most of you that do design work are probably saying, we don't like to see any more than 20 gallons a minute through a 1-inch line. Now, why would you want to have a smaller flow sensor than the line size? So that you can detect this lower minimum flow. And as you see, the minimum flow in a 3-inch line is 6 gallons a minute. If you dropped it to 1.5 inches, the minimum flow would be under 2 gallons a minute. So you design the flow sensor to be between the minimum and the maximum, and typically what I would say is try and put your largest zone somewhere in the middle third of this range.
And we had the same person had a follow-up question: is where can you get this chart easily?
This chart is it's on our website. If you go into our website and go into the product section and go into flow sensors, you will see a technical bulletin that has this chart right in it. So and at the end of it, our website is www.creativesensortechnology.com. Big word, but once you save it, you can go back to it easy enough and just go into the products and then the flow sensor part, and you can find that tech bulletin that shows flow ranges on it. One other thing maybe to point out at the bottom here, Dave, is that I've shown what kind of pressure drop there is in PSI at the maximum flow rates. And even if we're running a 1-inch sensor at 50 gallons a minute, there's only a 1/4 of a PSI pressure drop. So we're not going to lose any pressure in the system by undersizing a flow sensor. Okay. Let's go on to rule number 3, and that's if we're going to use one of these downsized flow sensors, how do we install it? And basically what we do is create what we're calling a meter run. And this meter run basically means we take our line size of the pipe, we reduce it, we know what the flow sensor size is going to be, we want to put our 10 diameters of straight pipe upstream and 5 diameters downstream into the meter, and then make our transition in size at the end of those measured nipples. So that if we went from 4-inch to 2-inch, we would have a 24-inch pipe nipple coming out of the flow sensor T on the upstream side. Then we'd make our transition, and this could be reducing bushing in a coupling or something of that nature, or actually a reducing fitting, and we'd do the same thing on the other side. And again, people question this. This is a generally acceptable practice in the hydraulic business. People question this and say, but aren't you going to have a tremendous loss of pressure in here? And you look at it and say, okay, we're probably talking about 3 feet of linear pipe. Look up in a pressure loss chart and think of the pressure drop that is usually shown as measured per 100 feet of pipe. Take 3% of that. So we really want to put these reducers far enough away from the pipe so that we get nice smooth flow through it, but there's nothing wrong with reducing pipe in this manner, and it'll work just fine.
And just noting, the velocity will be far greater in that little short 3-foot length than you allow elsewhere. Everybody thinks 5 feet per second. I can't go above that. Well, you can.
Yeah.
In the short length, you certainly can.
Yeah, think of the things, Dave, like the discharge of a booster pump. And typically, if you look at a centrifugal booster pump, you might have a 3-inch suction line coming into it and only an 1.5 inch discharge going out of it, and then you quickly go up to a 3-inch discharge let's say to accommodate 150 gallon a minute flow rate. There is no reason to worry about large or fast velocities over short distances. It's when it's over a long distance that it creates a problem. So you can do this. What I put in here too is also on our website for our flow sensor products, and certainly something that you might want to look at. We've put these frequently asked questions sections in the product section again, so that some of these questions are discussed in a little more detail or answered. And certainly for this webinar today, we don't have time to go into a lot of other installation technicalities, but just to let you know that these answers to questions are there, and certainly contacting me directly is always an option. Now, moving along a little bit here, I just want to briefly touch on some of the other products that we make that go along with the flow sensors. And a couple of these are devices that allow flow to be used with smart controllers, but sometimes we have little application questions that come up. And one of the most common ones was, how do I have one flow sensor and I have one point of connection, but I really have two irrigation controllers on this job. Is there a way to hook up a flow sensor to two controllers? And the answer is yes, but you have to be careful. Unlike a solenoid valve, you cannot just hook a flow sensor up to the flow sensor circuits on controllers. They are, number one, electronic circuits, and by that means they're usually a little more delicate than a operating circuit for a solenoid valve. And so we need an isolator, and we need something that will optically separate the signal so there's no cross feed from one controller to the other. Trying to hook up a flow sensor to two controllers simultaneously can do two things. One, it can damage the controller circuitry, or second, it can give you false readings, because some of these circuits are very sensitive to the current draw of the sensor, and by backfeeding it or cross-feeding it, as this is called, you can get into trouble with accuracy. So we made this little product called an IsoFlow. And what it does is it optically isolates the flow going to the two controllers, splits the signal, if you will, and allows it to be shared between two devices. I'm showing two irrigation controllers. It could also be shared between an irrigation controller and a pump control system, or an irrigation controller and a fertigation system, or even a fertigation system and a pump station. So it's an isolation device, but what we've done is gone a little further with it. It also has a little processor in it, because sometimes you need to outsmart the smart controller. If we have two irrigation controllers and they do not run at the same time, they have the ability to sense unscheduled flow. If controller A has started an irrigation cycle, but the flow is going to controller B will sense that as a break or an unscheduled flow event and go into an alarm mode. And if both of these are sharing control of a master valve, controller A may be calling for water, controller B may decide it's time to shut down the master valve. So we have some control inputs in here, and by hooking them up to the controller, we can sense which controller is active, and we can block the flow to the opposite controller. Of course, when neither controller is on, we want them both to be able to read unscheduled flow, and they can. And if both controllers are off, if they're off, they can both read unscheduled flow. If they're both active, they both read active flow. But it's when one is off and one is on that we get into this switching nightmare. So we have a way around that with the logic that's built into this device.
And I'm going to show some details for these situations when I do my presentation.
That's great, and I know that, so I'm just touching on these things at this point. As soon as we made the ISOFlow device that would split the signal in two, we had an irrigation consultant say, but I've got jobs where I have 3 or 4 or 5 different irrigation controllers. Think of an industrial campus or a homeowner association. Typically projects don't go in all at the same time. They go in phases, so there are controllers put in and then additional controllers added on as the build-out continues. So we came up with basically a larger version of the ISOFlow, the ISOFlow 306, which we call the ISO 6. This allows us to split that one flow sensor signal between up to 6 different controllers. And as long as one of them is running, it also contains that control logic that if one controller runs, the rest are shut off from flow. If 2 of them are active, 4 are shut off. If 3 of them are active, the other 3 are shut off, and so on, so that only the active controllers are receiving flow and the inactive ones don't go into an unscheduled flow alarm. So this is it's not a device that's going to be used a lot, or it's not going to be used obviously as much as a flow sensor, but it's a practical device that's there for those times when you need it. Now we do the same kind of a little device because another situation comes up more often than not, and that's that we have an irrigation system with more than one point of connection. So we made this other little transmitter, if you will, called a Combiflow. And what a Combiflow does is it allows us to combine signals from 2 different flow sensors, process those signals to a rate of flow, and then send an output as a single flow into the irrigation controller. Most irrigation controllers only have one flow input. So if we have 2 sensors, there's no way for this controller to read both of them without a device like this. The beauty of the Combiflow is that it doesn't require that the sensors be the same size or the same type. Each one is independently programmed as to what its size and calibration information is. And then we pick a third independent output, and we calibrate that so that it will join up with what the flow sensor input is set to in the clock. Where does this come in? Why do we have 2 flow sensors? Well, probably the most common that we talk about is 2 points of connection. Again, most projects, anything from a park to a housing, homeowners association, to a college campus, they put in irrigation systems piecemeal. They don't do a campus-wide type of system installation, and usually we get to a point where we're putting in one system runs off of one point of connection, joining with another system that runs off a second point of connection. When we do that, we may also loop the main lines between the 2 systems to improve hydraulic characteristics, and we find that maybe in addition to the 2 points of connection, we have systems that are looped, and certain parts of the system can be fed from either side of the loop. Therefore, we need 2 flow sensors. The other thing that has become increasingly prevalent in alternative water sources is that we have a potable water source at one point of connection with a flow sensor on it, and we have a flow sensor on our rainwater harvesting source or our reclaimed water pipeline or something like that, so that we can measure both of them. We may totalize them separately, but in terms of the smart controller, we still want to have both signals feeding in for all of our flow rate protection programs. All of our alarm protections require measuring both. The Combiflow will put out a signal out of it regardless of whether one source is running, both sources are running, or the other source is running. So you always get some indication into the smart controller as to what the total flow being used by the system will be. So those are. I got one other little product to show you. This is not usually something that's specified or drawn on the plans of an irrigation system, but something that we like to point out to people that makes a great tool to include in a job when you're putting together an irrigation system. There's usually a list of spare parts or service devices, and this is a little flow sensor simulator. It's a great little product that just connects. It's a handheld product, doesn't have batteries in it or anything, connects to the flow sensor input of the controller, and it makes it great to demonstrate flow functions, but more importantly to the installer or the manager, you can test the installed wiring, you can check controller flow sensor setup, and if you do have problems in the field, it makes it a great troubleshooting tool. So I just throw that in there again, and again, that's on our website as well. So that's a very, very quick kind of high-level overview of our product line. I know Dave is going to go into actually how you use the LandFX software to incorporate this into a design, but just things out there. If there are other questions, you certainly can visit our website. You can email us at info@creative-sensor-technology or call on a phone number, and I can make all of this information available to all of you, as I'm sure Dave can as well. So that's my portion of the webinar, and I'm going to now turn the microphone back over to Dave, unless you've got any other questions that came in for me, Dave.
No, we don't have any questions right now, and so I would like to spend actually just a very short period of time showing how to utilize LandFX and how you would typically put in a flow sensor and master valve on a particular project. Now, this isn't a project, there's no head, but what I've done is I've put 3 caps here, and each pipe cap has a certain flow that's required of it. So you know, these 2 on the left and the right are 32.5 GPM each, and the one up above is 20 GPM. All total, that would be 70, 80, 90 GPM total that this whole thing is going to require. So it's like a whole bunch, of valves are somehow demanding 90 GPM. So what I've done for the point of connection, and I'll go to the irrigation manager, for the point of connection, I have a 2-inch point of connection water meter, and that's giving me a total with all of this particular breakdown of 108 GPM. So I've got it cured, and that's my maximum flow available. And I want to get a flow sensor that will match that maximum, also my minimum. Now, I'm not showing on my plan my minimum, but I'm going to pretend I have some drip systems, and some of them could be as low as, let's say, 3 GPM for this drip system. So I want to make sure I can go from a minimum of 3 GPM to a maximum of 108 on there. I'm going to put some pressure in here. Let's say I have 85 PSI here. So I've done that. Now let me add a flow sensor to this project. I've already added a master valve to the project. I've already added to this project a backflow device and a controller, and I've placed the controller on here. I'm going to add a flow sensor, and it is not necessarily a head or a valve. It is auxiliary equipment, and if I expand the list of auxiliary equipment, I can see there's a flow sensor category there. I can pick it here and add, or if I'm not picking any category and I'm in auxiliary equipment and I say new, I see that list again, because we need to know what kind of equipment you're adding, and the kind I'm adding is a flow sensor. I say OK. I see manufacturers in the system that have flow sensors. Right here at the top is CST. I click on that, and I can see some of the things that Norm was talking about. Here's an ISOFlow and a Combiflow processor. If I scroll down a little bit, I can see these 2 down here are the real common flow sensors, a saddle type, and it says 3 to 4 inches. So obviously that would be a bigger system. And then the real typical one is this T-type flow sensor. Both of those are very common. The T-type probably, in my mind, will be the most common. I'm not sure what size to make it, but let me just click on that and see what I've got. I've got 3 options here, a 1 inch, an 1.5 inches, and a 2 inch. And then we remind you what the flow ranges are for each one of those. You can see at the end here. And we remind you that here when you're selecting it, when you're placing it, at every step of the way, and put it into its description in the schedule. Because those are very important numbers. And you can see the 1 inch has a low of 0.86 GPM and a high of 52 GPM. So that is really low. And that, I think, is the unique thing about CST, is how it can respond to extremely low flows, and we have those with drip systems. My example was I had 3 GPM on some drip system as a low, and I had 108 GPM, or actually it was 90 GPM is what my system is going to require. Its capability is about 108, you know, as a 2-inch meter. It could be this 1.5 inches. I could even use, if I wished to, this 2-inch one. Now, Norm, I'm going to ask you, given my situation, I have 3 GPM is my absolute minimum. I have 70 GPM is my system design, but my source could allow a little bit over 100. So technically, which one of these would you pick, an 1.5 inches or 2 inch?
Well, that's going to be a little bit of a question, Dave, that you know, either one of them, I would say, would probably handle your requirements, because your requirements are higher than the minimum flow of the 2-inch one. Your minimum flow is higher than 2.8 by a little bit, and your maximum flow is lower than both the 2-inch and the 1.5 inch maximum. So probably from rule of thumb, what I would do is try and look at the system and the scheduling and say, how often am I going to be running at full flow compared to how often am I running at lower flows? And
Okay.
if I had, let's say, one zone out of 30 that was up in the 70 or 80 gallon a minute range, then I'd probably go with the smaller sensor. But if I had 25 or 30 of those zones running at the higher end of the range and only 1 or 2 at the lower end, then I'd probably go with the larger sensor.
Okay, so I'm going to give you my scenario, and I'm making this up as I go. I'm going to say about half of this stuff is drip, and about half of it is pretty high flow. You know, turf, like it's a sports field and park area. But in the park area, the shrub areas are, let's pretend, mostly drip, and the lawn areas are just bigger lawn areas, so they're going to take a larger. So let's call it half and half. Half of it is extremely low flow. Half of it is you know, pushing in the you know, let's say 50 to or greater, 50 to 70 GPM. Mm-hmm. So which one would you pick? I'll let you pick it.
Yeah, again, I think what I would do in a case like that is that, you know, where your maximum that we talked about is about 70 GPM. Again, that doesn't really exceed 10 feet per second. So we're not right up against the end of our flow range. We're still, you know, about 2/3 of the way up. I'd probably go with the 1.5 inch sensor.
Okay, That sounds good to me. But I wanted to get all that logic out there for the people. So
Okay.
let me add this 1.5" sensor to my project. And now let me place some of this stuff. And again, I looked at the meter, and it was a 2". And I'm going to pretend the meter's down here. So I have to place that meter. I'm going to place auxiliary equipment. There's my water meter. And I'll drop it in, and let me pretend it's in the sidewalk here. After the water meter will be my backflow device, and you may say, what is the size of the backflow device? Just bear in mind, I'm going to view data for that. This is a Febco 825Y, and I tend to go to whatever says specification sheet on darn near anything. That's the way it tends to go. Here's the specification sheet, and let me zoom in on this particular spec. Similar, I think, to the flow sensor, the backflow device, people often oversize. Now, I had a maximum of 100, let's say, GPM. It was sort of like 70, but my point of connection will allow 100. And I can see that I don't necessarily, but this becomes an optional thing too, don't necessarily want, oh, I need a, because really 100 GPM, the piece of pipe that is going to be connected to that at 5 feet per second would be a 3-inch pipe. A 3-inch pipe at 5 feet per second is about 108. At 4.2 is about 90. So you go, oh my, I want a 3-inch backflow. Not necessarily has to be the same size, because you can see on this 1.5" here at 100 GPM, I'm losing halfway between, say, 10 and 15 psi, the loss through it, roughly 12.5. If I go down to the 2-inch at 100, that's right here, it's actually slightly higher than the other one, just slightly higher. And it's because, quite frankly, the 2-inch has a bigger spring in it, and there's it needs a little bit more loss to take that same pressure through. So size doesn't often translate to these. So I think you would be fair picking either 1.5" or 2-inch, maybe similar to the other thing with the flow sensor, for a particular backflow device. I'm going to pretend I'll pick a 2-inch backflow device and stick it right here, pretty close to the meter, as close as reasonably possible. And now, after that, I'm going to have my master valve and my flow sensor, and as Norm indicated, it's arbitrary as to which one goes first. I think I'll just, for the sake of argument, I'm going to place a valve and put my master valve in there. I'd do the same thing. I'd look at the data and say, what are the sizes I'm talking about, and I'm going to pretend a 2-inch master valve probably works fine, or actually 1.5". I'm going to make it the same size as my flow sensor here, and I'll just call it, maybe I'll call it MV for master valve on here. And then after that is going to be my flow sensor. So I'm going to go to place. It's not a valve or a head, it's auxiliary equipment. There's my flow sensor I added. It was a specific one on there, and I'll drop that in right here, and I'll just give it F to indicate what it is on there. And this is a very typical point of connection. It's a whole buildup of several things on there. And the piping for this is going to be draw a pipe, and I'm going to draw my mainline pipe. I obviously would connect from my meter, and I would go to my backflow device, to my master valve, to my flow sensor, and then I would come up and I'll go to these particular little caps up here, which are going to be putting a demand on this. And I have one more up here. So actually there is demand on this particular system, so that if I were to size this system, and I'll go ahead and size the main line, and I'm going to size it single valve operating at a time, and just say OK. And I've sized it. I have actually a 2-inch line here and only 1 1/4 inches going up to this 20, but roughly a 2-inch line with a total of 68.25 PSI and 32 GPM coming out of that. Oh, it's going 32 to each one. It's assuming 1 valve at a time. Let me operate it at more than 1 valve at a time. Multiple valves, I'll just run it up to the 108, or I could make this less. I could make this like 90. So it's sized it. It's going to be more like a 4-inch piece of pipe coming out of there, something like that. And then it's going to break off to 1.5 inches in one way and a 2-inch going in the other directions. So the moral of the story is that this size can be quite large compared to your flow sensor. And so what do you do about details for this? I'm going to go to my flow sensor right here, and I want a detail for it. So I'm going to click detail. It takes you in our system where flow sensors are, but you're going to want to navigate on that. And where you're going to want to navigate to is to maybe you've saved flow sensors details somewhere, but where you have in your system, and you may not know it, there's something called under this upper category called details, and this is however you define them. There's something called FX detail library. If you expand that, you'll have irrigation. If you expand that, you'll have CST down here. And if I go to CST, I have flow sensor, and I'll click browse. I have it for, this is the T-mount. This is the one that Norm was showing you earlier. It shows the pipe diameters, it shows the direction of the flow, the type of wire, and then there's a saddle mount type showing basically the same thing, but we were looking at, I believe, 3- and 4-inch pipe on there for the saddle mount. So you have these details, and you can assign them, you can open them, you can come here and say, you know, I can browse, I can open that up, I can assign it, I can do a lot of things to there. We also have details, and then Norm had showed the ISOFlow, and let me browse in there. This is with multiple controllers, normally closed or normally open master valve situations. These become more exotic, but if you do more exotic things, you're going to really appreciate these details because they're quite thorough, quite well done, and will make it very clear to the contractor how to install this particular setup, this particular flow sensor setup with more than one controller, and in this case a normally open master valve, that kind of thing. Also, there's the Combiflow, which is dealing with multiple flow sensors and a controller, and in this one there's a little bit different situation. So you can look over those. There's a detail to match your needs in here for a variety of situations. Another place we have details is in irrigation. We have FX details, which are not relating to any particular manufacturer. I noticed earlier we did have under master valves. Let me browse in there. I have some that do relate to this one right here, related to a master valve and a flow sensor situation. Let me open it up just to look at it. Because it's sort of typical, this is coming from a backflow, and this is in this particular situation was physically a 4-inch pipe, and it came down to a master valve that was it says that specified, but that was a 2-inch master valve because it has a little 2-inch nipple right here, and then there's a length of pipe that is 2-inch, there's the flow sensor, then a length of pipe leaving it, and then it bumps back up to a 4-inch main line. And that's a fairly typical situation with pipe diameters in between them of clear pipe, of a larger pipe at each end, going down to a smaller situation here. So that is fairly common in that. For my thing, I'm going to add this creative sensor technology, this flow sensor, this T-mount, and say, okay, and now that detail is associated, and if you didn't have it, which you won't, perhaps, it'll automatically be downloaded to your system. You can actually open those details up in that FX detail library, open each one up, kind of view it, and go, I really like that one. Let me save it to a location that makes sense to me, and then turn around and save it with our system. But those details are quite valuable, and I've assigned a detail to it. But this sort of combination of things going on here is pretty common in today's world, and you should become familiar both with master valves and flow sensors and how they interact with the system. And then smart controllers, as Norm's detail showed, the controller can be 2,000 feet away, which is quite a lengthy distance. Mine happens to be up here by the building, not terribly far away, but that's perfectly fine. It doesn't have to be right there with the equipment. And I'll just simply run a wire from, obviously the controller to the flow sensor on there. So that's basically how to add those to a project and how to bring that kind of thing into the system and visualize the system. Let me look to see if we have any other questions here. I don't have any questions. Did you have any comments, Norm?
No, I think that what you have just explained, Dave, kind of ties things together and shows, how you can take the information that maybe I discussed briefly and apply it to the plan. So I think from this point on, really what all we can offer is to say, if you have additional questions, make sure and get a hold of us. We'd be glad to help with special applications or things that are unique to a certain job. We're a phone call or an email away.
Well, thank you, and I want to thank Norm for participating and letting everybody know about flow sensors and how they work and how his flow sensors work. And I want to wish everybody a great weekend, and thanks for joining the webinar. So we'll see you later, Norm.
All right. See you later, Dave. And to you that attended, thank you for your time. I hope you have a nice weekend, too.
All righty. Goodbye.
Bye.